A vast volcanic structure rises silently beneath a stretch of sea bordered by Italy, its presence largely absent from public awareness despite its immense scale and potential implications. How can a mountain larger than many on land remain hidden in plain sight? How does a system of molten rock operate under thousands of feet of water pressure without revealing itself at the surface? And more importantly, what does it mean for nearby coastlines when such a structure exists in a state that is still not fully understood? Far below the surface of the Tyrrhenian Sea lies Marsilli Seamount, an enormous underwater volcano extending across a significant portion of the seafloor between southern Italy and the deeper basins of the central Mediterranean. Stretching roughly 70 kilometers in length, which is about 43 miles, and spanning close to 30 kilometers in width, or around 19 miles, this submerged structure dominates the region's underwater landscape. From its base on the ocean floor, it rises nearly 3,000 meters, approximately 9,800 feet, forming a towering volcanic edifice that would rival many of the prominent mountains found on land if it were visible. Despite this immense vertical reach, its summit remains concealed beneath the sea, resting at a depth of roughly 450 to 500 meters, or about 1,500 to 1,640 feet below the water's surface. This means that, even at its highest point, it never breaches the ocean above, maintaining its hidden state while continuing to evolve geologically. Its invisibility contributes to the difficulty of studying it, as direct observation is limited and dependent on specialized marine exploration technologies. The geological setting in which Marsilli exists is defined by the ongoing interaction between major tectonic plates beneath the Mediterranean region. The boundary between the African plate and the Eurasian plate creates a dynamic environment characterized by subduction, extension, and localized zones of magma generation. In the case of the Tyrrhenian Basin, the tectonic processes are particularly complex. Rather than a simple collision, the region experiences a form of back-arc extension where parts of the crust are being pulled apart behind a subduction zone. This stretching of the crust allows magma from deeper layers of the Earth's mantle to rise toward the surface, forming volcanic systems both above and below the sea. Marsilli Seamount is part of a broader volcanic arc associated with this tectonic activity, but it stands apart due to its size and relatively recent formation compared to older volcanic structures in the region. Geological evidence suggests that the volcano has been active over hundreds of thousands of years, with successive eruptions building layer upon layer of volcanic material. These materials include basaltic lava flows, fragmented volcanic debris, and ash deposits that have accumulated to create the massive structure observed today. Unlike many terrestrial volcanoes that exhibit steep, well-defined slopes, Marsilli's flanks are shaped by a combination of eruptive processes and gravitational forces acting underwater. The presence of seawater significantly influences how magma behaves during eruptions. When magma emerges at such depths, the high pressure exerted by the overlying water suppresses the formation of large gas bubbles, reducing the explosiveness typically associated with volcanic eruptions on land. Instead of violent explosions, eruptions tend to produce pillow lavas, which are rounded, bulbous formations created as molten rock rapidly cools upon contact with cold seawater. Over time, these pillow lavas accumulate and stack upon one another, gradually constructing the volcano's bulk. However, this method of growth also contributes to structural weaknesses. The rapid cooling process can trap fractures and voids within the rock, while layers of loose volcanic debris may remain poorly consolidated. As a result, much of the volcano's structure consists of materials that are less stable than the solidified lava flows found in some land-based volcanoes. Another critical factor influencing the stability of Marsilli is hydrothermal alteration. Seawater circulates through fractures in the volcanic rock, interacting with heat from underlying magma. This process alters the chemical composition of the rock, often weakening it further by transforming solid minerals into softer clay-like substances. Over extended periods, these alterations can significantly reduce the mechanical strength of the volcano's internal structure, making it more susceptible to deformation or collapse. Beneath the visible structure lies the volcano's magma system, which plays a central role in its ongoing activity. Magma is generated in the mantle due to partial melting caused by changes in pressure and temperature associated with tectonic processes. This molten material then rises through the crust, accumulating in reservoirs at various depths. These reservoirs are not static. They can expand, contract, and migrate depending on the supply of magma and the pressure conditions within the system. The movement of magma within Marsilli is believed to occur through a network of conduits and fractures rather than a single centrally defined chamber. This distributed system allows magma to reach different parts of the volcano, contributing to its elongated shape along the sea floor. Seismic activity detected in the region indicates that magma movement continues to occur, suggesting that the volcano remains active even if eruptions are not directly observed at the surface. Gas emissions also provide clues about the internal state of the volcano. Dissolved gases within magma, such as carbon dioxide and sulfur compounds, can escape through fractures and vents on the seafloor. These emissions are often detected as plumes rising through the water column, sometimes accompanied by changes in temperature and chemical composition of the surrounding seawater. Such signals indicate that the volcanic system is still releasing energy and material from below, even in the absence of visible eruptions. The interaction between magma and seawater creates additional complexities. When magma comes into contact with water, rapid cooling can lead to fragmentation, producing fine volcanic particles. In certain conditions, this interaction can generate localized explosive activity, though it is typically less intense than eruptions occurring in shallow water or on land. These processes contribute to the accumulation of loose material on the volcano's slopes, further influencing its stability. The shape and structure of Marsilli reflect a long history of such interactions. Its elongated ridge-like form suggests that volcanic activity has been guided by underlying tectonic features such as faults and fractures within the crust. These structures provide pathways for magma to rise and also influence how the volcano responds to stress. Over time, the continuous addition of volcanic material combined with tectonic forces has created a complex and uneven internal architecture. One of the most significant aspects of Marsilli's geology is the balance between construction and destabilization. While eruptions add new material to the volcano, increasing its size, other processes work to weaken and reshape it. Gravity acts continuously on the massive structure, pulling on its flanks and creating stress within the rock. When this stress exceeds the strength of the material, deformation can occur, leading to landslides or partial collapses. Evidence of past slope failures has been identified through mapping of the seafloor surrounding the volcano. Deposits of displaced material extend outward from its base, indicating that sections of the volcano have collapsed in the past. These events may have occurred gradually or suddenly, depending on the conditions at the time. The presence of such deposits suggests that instability is an inherent feature of the volcano's evolution. The potential for future instability is closely tied to the ongoing activity within the magma system. As magma accumulates beneath the volcano, it can increase pressure within the structure, causing it to expand or deform. This process, known as inflation, can weaken the surrounding rock and create conditions conducive to collapse. Conversely, the withdrawal of magma during eruptions or internal redistribution can lead to deflation, which may also destabilize the structure by reducing support from below. Seismic monitoring has revealed patterns of small earthquakes in the region, often associated with magma movement or adjustments within the volcanic structure. These seismic signals provide valuable information about what is happening beneath the surface, but they are limited in their ability to predict specific events. The underwater environment complicates the placement and maintenance of monitoring equipment, resulting in gaps in the data that would otherwise help to build a more complete understanding of the system. Another layer of complexity arises from the broader tectonic environment of the Tyrrhenian Basin. The region is characterized by a combination of compressional and extensional forces, creating a dynamic setting where the crust is constantly being reshaped. Faults within the crust can interact with the volcanic system, influencing both the movement of magma and the stability of the volcano itself. These interactions mean that Marsilli cannot be considered in isolation. It is part of a larger network of geological processes that extend across the Mediterranean. The depth at which Marsilli exists also affects how energy is transmitted during volcanic or structural events. Water acts as a medium that can absorb and redistribute energy, altering the way seismic waves propagate and how disturbances are felt at the surface. This can make it more challenging to detect and interpret signals associated with activity at the volcano, further contributing to the uncertainty surrounding its behavior. Mapping efforts using sonar and other remote sensing technologies have provided detailed images of the volcano's shape and surface features. These maps reveal a landscape marked by ridges, depressions, and channels formed by past volcanic activity and mass movements. However, even with advanced technology, much of the internal structure remains hidden, leaving unanswered questions about how the volcano is organized beneath its outer layers. Activity beneath Marsilli Seamount does not follow the familiar patterns often associated with volcanoes rising above land, and that distinction becomes most important when considering how risk develops in such an environment. The structure continues to evolve under constant pressure, both from the weight of the overlying water and from the internal forces generated by magma movement. These competing influences shape not only how the volcano grows, but also how it may eventually fail. One of the defining characteristics of Marsilli is the imbalance between its rapid construction and its long-term stability. Over time, repeated eruptions have deposited vast amounts of volcanic material, building an edifice that rises nearly 3,000 meters, or about 9,800 feet from the sea floor. However, the rate at which this material accumulates has outpaced the processes that would normally strengthen and consolidate it. Much of the structure remains composed of fragmented deposits, loosely packed layers, and rock that has been chemically altered by circulating seawater. This imbalance creates zones within the volcano where strength varies significantly from one area to another. Some sections consist of relatively solidified lava, capable of supporting substantial weight, while others are made up of weaker, more porous material. Over time, stress becomes unevenly distributed throughout the structure. Gravity continuously pulls downward on the massive slopes, while internal pressure from magma can push outward or upward, creating a dynamic system where forces are rarely in equilibrium. As these stresses build, deformation begins to occur. This may take the form of slow creeping movement along the volcano's flanks, where sections gradually shift under their own weight. Such movement is often too subtle to detect directly, especially beneath hundreds of meters of water. However, it plays a critical role in weakening the overall structure. Small fractures can expand and previously stable areas can become increasingly unstable as the internal framework of the volcano adjusts to ongoing stress. At times, this gradual deformation can transition into more abrupt events. When a section of the volcano reaches a critical point, where the strength of the material can no longer support the forces acting upon it, failure can occur. This failure may involve the sudden collapse of a portion of the slope, sending large volumes of rock and sediment downslope into the deeper parts of the Tyrrhenian Sea. These events, known as submarine landslides, are among the most significant hazards associated with underwater volcanoes like Marsilli. The mechanics of such a collapse are influenced by several factors working together. One key factor is the presence of hydrothermally altered rock, which tends to be weaker and more prone to failure. Another is the accumulation of volcanic debris that has not been fully compacted or cemented. Additionally, the intrusion of magma into the structure can create zones of elevated pressure, effectively pushing against the surrounding rock and reducing its stability. Even relatively small changes in pressure or structural integrity can be enough to trigger a collapse when conditions are already close to failure. When a large section of the volcano collapses, the immediate consequence is the displacement of seawater. Unlike surface eruptions where energy is released into the atmosphere, a submarine collapse transfers energy directly into the surrounding water. The sudden movement of material forces water outward and upward, generating waves that can travel across the sea. The scale of these waves depends on the volume of material involved and the speed at which it moves. In scenarios where a significant portion of Marsily's flank were to fail, the volume of displaced water could be substantial enough to produce a tsunami. Such waves would propagate rapidly across the surrounding basin, potentially reaching the coastlines of southern Italy, including regions near Sicily and Calabria. Given the relatively short distances involved, travel times could be on the order of tens of minutes, leaving limited opportunity for warning or response. The behavior of these waves would be influenced by the shape of the seafloor and the coastline. As tsunami waves approach shallower water, their speed decreases while their height increases, concentrating energy along the shore. In certain situations, this can lead to significant wave heights, particularly in areas where the seafloor channels energy towards specific points along the coast. The complex marine topography of the Tyrrhenian Basin means that wave impacts could vary widely depending on location. Despite these potential risks, predicting when or if such an event might occur remains extremely challenging. The monitoring of Marsili is constrained by its underwater location. Instruments must be deployed on the seafloor or rely on remote sensing techniques, both of which have limitations in terms of coverage and continuity. While seismic activity can be detected, providing indications of magma movement or structural adjustments, these signals do not always translate into clear warnings of impending collapse. Efforts to map and study the volcano have revealed patterns that suggest ongoing activity. Areas of gas emission indicate that magma remains active beneath the surface, releasing gases that rise through the water column. Temperature anomalies in localized areas suggest the presence of hydrothermal systems, where heated water circulates through rock. These signals collectively point to a system that is far from dormant, continuing to evolve beneath the sea. The broader tectonic environment also plays a role in shaping Marsili's future. The interaction between the African plate and the Eurasian plate continues to drive processes within the Mediterranean region. In the Tyrrhenian Basin, this interaction is expressed through a combination of subduction and extension, creating conditions that favor the continuation of volcanic activity. Faults within the crust can shift in response to these forces, potentially interacting with the volcanic system and influencing its stability. Another aspect to consider is the long-term evolution of the volcano. Over geological timescales, structures like Marsili can undergo cycles of growth and collapse, gradually reshaping themselves as material is added and removed. Each phase of activity leaves behind evidence in the form of deposits on the seafloor, building a record of past events. By studying these deposits, it becomes possible to gain insights into how frequently collapses have occurred and how large they may have been. However, this record is incomplete, and many details remain uncertain. The underwater environment preserves some features while obscuring others, making it difficult to reconstruct a complete history of the volcano's behavior. This uncertainty adds to the challenge of assessing risk, as it limits the ability to identify patterns that might indicate future activity. Technological advancements are gradually improving the ability to observe and understand systems like Marsili. Autonomous underwater vehicles, improved sonar mapping, and more sensitive seismic networks are providing new data that was not available in previous decades. These tools allow for more detailed imaging of the volcano's structure and more precise detection of activity beneath the surface. Even so, the vastness of the ocean and the depth at which Marsilea exists mean that complete coverage remains difficult to achieve. The importance of continued observation lies not only in understanding the volcano itself, but also in recognizing how it fits into the larger system of geological hazards in the region. The Mediterranean basin is home to numerous active and potentially active volcanic structures, both above and below the sea. Marsilea stands out because of its size and its hidden nature, but it is part of a network of processes that collectively shape the region. If you found this deep dive into one of Europe's most hidden geological giants insightful, take a moment to like, share, and subscribe. Tap that hype icon to help this reach a wider audience and keep more people informed about the powerful forces shaping our world beneath the surface.